All right, my friends, let's take a look at part B here. So notice that it's already written. So you've got the alternating part and then you've got the non-alternating part. So no need to do that part. You should introduce, though, that a sub n, your non-alternating part, is the 1 over n piece. So mention that, since we'll be assuming that the reader knows that they are one and the same as we continue. Okay. So for the first thing we want to check is that a sub n, if it's defined as 1 over n, is it always positive? So you do need that non-alternating part to be always positive. I hope it makes sense. It is. If you plug in anything from 1 to infinity, you're just plugging in positive numbers there. And so it is. So 1 over n is greater than 0 for all n greater than or equal to 1, which those are the only ones we need to worry about anyway. So you've got that. The next thing you want to make sure is that the limit as n goes to infinity on the non-alternating part, that it is indeed 0, and it is. Now for the fun part, figuring out how to show in a somewhat kind of mini proof style that this non-alternating part is decreasing. Now, if you weren't asked to show it, and I am asking you here, but there will be times when you're not asked to show it, you'll just need to kind of like in your mind check it off that it's true. And just expanding the terms of 1 over n should show you that it is indeed decreasing. But let's make sure, let's kind of show the scratch work and then show how to write it kind of in a mini proof style as well. Okay, so we basically need a sub n plus 1 to be less than a sub n if we're going to show that it's decreasing. And then if a sub n is defined as 1 over n, then what would a sub n plus 1 be? It would be, 1 over n plus 1. Now, fun fact, if you have these two fractions and they're less than each other, then if you were to like reciprocate both sides, then it would kind of reverse the direction of the inequality. If that doesn't make sense, you could actually multiply both sides by n plus 1 and multiply both sides by n, and stuff like that, which is all positive. It wouldn't, because n is from 1 to infinity. So you could also do that. So you could multiply both sides, by n times n plus 1. Right? Like you could totally do that. And then you'd end up with n is less than n plus 1. And then you could subtract n from both sides and you'd end up with 0 is less than 1. And right there, my friends, that would be a really good universally true statement to start off with. And, so you could say something like clearly. And let me tell you about the word clearly. When your professor writes clearly on the board, it really makes people feel intimidated and not want to ask questions that I should have asked that day. It took me like a week and a visit to the professor's office to figure out how they started off on that step right there. Anyway, so clearly 0 is less than 1. And then if you add n to both sides, the inequality would still hold true. So see how I'm just like working my way up, right? And then I personally don't like to do this multiplication garbage. I really like to just reciprocate both sides and flip the inequality sign. So 1 over n would be greater than 1 over n plus 1. And why is that okay? Because if you divide by a bigger number, you get a smaller number. That's why. Anyway, so hopefully that makes sense. And then 1 over n is a sub n. 1 over n plus 1 is a sub n plus 1. And then you've got it, right? So a sub n is bigger than the term right after it, right? And we did this in terms of n, so it'd be true for all n values. And so your conclusion would be, therefore, a sub n is decreasing for all n greater than or equal to 1. There we go. Okay. So you've got all three things, right? You've got terms are positive, terms go to 0, terms are decreasing, and that's all it takes. Those three criteria are met. Therefore, we could say the sum as n goes from 1 to infinity of -1 to the, what did it say? N minus 1 times 1 over n is convergent by the alternating series test. There we go. So hopefully you're feeling like you've kind of getting the feel for it. Now, a comment, I want you guys to notice, it turns out a sum that looks like this has a special name. So the sum as n goes from 1 to infinity of -1 to the n minus 1 times 1 over n. Well, what would this sum have been called if it didn't have the non-alternating part, if it only had 1 over n in it? Yeah, that would have been the harmonic series. And the harmonic series diverges, if you recall. But it turns out that if you have this alternating part on it, then all of a sudden it converges. And if you were to expand this out and notice that having alternating signs of plus, minus, plus, minus, plus, minus, it actually makes it easier for a series to converge if it's alternating because of kind of the canceling out aspect of having some positive and some negative terms. So the funny name or the cute name for this one is called the alternating harmonic series. And while the harmonic series diverges to infinity, the alternating harmonic series actually converges. Now you'll find that we can't actually figure out exactly what it converges to. The best we could do with something like this would be to approximate it, but we can say that it converges. It adds up to something finite. We probably won't be saying exactly what it is, but it adds up to something finite. All right, my friends, that's it for part 1 of section 8.5. And then in part 2, we'll move to classifying a convergent series as absolutely or conditionally convergent and using the alternating series remainder to approximate the sum of an alternating series.